Let us understand the world of Wi-Fi standards. We will explore the evolution and implementation of wireless networking technologies. We will discuss the IEEE 802.11 protocol family, understand the performance characteristics, touch upon the security considerations, and explore the implementation best practices. Here's a timeline showcasing the evolution of Wi-Fi standards. In 1997, we had the 802.11 legacy standard operating on the 2.4 GHz band, providing 1 to 2 megabits per second using direct sequence spread spectrum and frequency hopping spread spectrum. In 1999, 802.11b arrived, still on the 2.4 GHz band, but boosting speeds up to 11 megabits per second, utilizing direct sequence spread spectrum. Also in 1999, 802.11a entered the scene, now on the 5 GHz band, achieving up to 54 megabits per second with orthogonal frequency division multiplexing. 2003 saw the introduction of 802.11g, working on the 2.4 GHz band, delivering up to 54 megabits per second with orthogonal frequency division multiplexing and direct sequence spread spectrum. 2009 brought 802.11n, also known as Wi-Fi 4, operating on both 2.4 and 5 GHz bands, reaching up to 600 megabits per second with multiple input multiple output technology. In 2014, 802.11ac or Wi-Fi 5 emerged, exclusively on the 5 GHz band, providing up to 3.5 gigabits per second using multi-user multiple input multiple output. Finally, in 2019, 802.11ax or Wi-Fi 6 arrived, using 2.45 and 6 GHz bands, achieving speeds up to 9.6 gigabits per second with orthogonal frequency division multiple access and 1024 QAM. Now let's explore the 802.11 protocol architecture. Starting from the top, we have the application layer followed by the transport layer, and then the network layer. The data link layer is next, which is further divided into two sublayers: the logical link control and the media access control. And finally, we have the physical layer. It is important to remember that 802.11 standards primarily define the media access control and physical layers of the open systems interconnection model. The media access control layer handles channel access control mechanisms and frame formatting, while the physical layer defines radio transmission methods such as direct sequence spread spectrum and orthogonal frequency division multiplexing. The upper layers remain compatible with standard transmission control protocol/internet protocol networking, ensuring seamless integration with existing wired networks. Let's examine the frequency bands used in Wi-Fi communication. First, we have the 2.4 GHz band, which ranges from 2.4 to 2.4835 GHz. It includes 3 non-overlapping channels, specifically channels 1, 6, and 11. It offers greater range but is more prone to interference, and is utilized by the 802.11b, G, N, and AX standards. Next, we have the 5 GHz band, covering the range from 5.15 to 5.85 GHz. It supports up to 24 non-overlapping channels, offers higher speeds and experiences less interference. It is employed by the 802.11a, NAC, and AX standards. Lastly, there's the 6 GHz band, which spans from 5.925 to 7.125 GHz. It provides up to 59 non-overlapping channels, delivering the highest speeds with the least congestion, and is used by the 802.11ax, Wi-Fi 6E, and newer standards. Next, let's discuss the modulation techniques used in Wi-Fi. The first technique is direct sequence spread spectrum. This spreads the signal across a wide frequency band, making it resistant to interference. It is used in 802.11b, supporting speeds up to 11 megabits per second, offering better range in noisy environments, and is more resistant to multipath effects. The second one is orthogonal frequency division multiplexing. This splits the data across multiple subcarriers to increase throughput and efficiency. It is used in 802.11a, G, N, AC, and AX, enabling higher data rates up to multi-gigabits per second and providing better spectral efficiency. Next is quadrature amplitude modulation. This combines amplitude and phase modulation to encode multiple bits per symbol. Higher-order quadrature amplitude modulation such as 256QAM and 1024QAM are used in newer standards, which allows more bits per symbol that results in higher throughput, but requires better signal quality, which is signal-to-noise ratio. The final one is multiple user, multiple input, multiple output, and orthogonal frequency division multiple access. These are advanced techniques for simultaneous multi-user communication. Multi-user, multiple input, multiple output allows multiple users simultaneously on different spatial streams, while orthogonal frequency division multiple access subdivides channels for multiple users. These are key features in Wi-Fi 5 and 6 for improved efficiency. Now, let's explore the channel access methods used in Wi-Fi networks. First, we have carrier-sense multiple access with collision avoidance. This involves listening before transmitting, also known as carrier sensing. If the channel is busy, the device waits for a random back-off time. Acknowledgement packets are used to confirm successful transmission. It is fundamental to all 802.11 standards and helps prevent hidden node problems. The second method is request-to-send/clear to send mechanism. This is an optional mechanism to reduce collision probability. The sender transmits a request-to-send frame before sending data. The receiver responds with a clear-to-send frame if the channel is clear, and other stations defer transmission. It is especially useful for large frames and in scenarios with hidden nodes. Let's review the security protocols used in Wi-Fi networks. The first is wired equivalent privacy, introduced in 1997. It was the first security protocol for Wi-Fi networks, designed to provide confidentiality comparable to wired networks. It uses the Rivis cipher 4-stream cipher for encryption, a 24-bit initialization vector, and static keys that rarely change. It is vulnerable to various attacks like FMS and chop attacks, and can be cracked in minutes with modern tools, and therefore it is deprecated and highly insecure. The next is Wi-Fi Protected Access and Wi-Fi Protected Access 2, introduced in 2003 and 2004 respectively. Wi-Fi Protected Access was developed as a replacement for wired equivalent privacy. Wi-Fi Protected Access 2 further improved security and became the industry standard. Wi-Fi Protected Access uses temporal key integrity protocol encryption, which is an improved Rivis cipher 4, while Wi-Fi Protected Access 2 uses advanced encryption standard counter-cipher mode with blockchaining message authentication code protocol encryption, which is much stronger. There are two authentication modes: personal, which uses a shared passphrase, and enterprise, which uses 802.1x/extensible authentication protocol, providing individual credentials. Wi-Fi Protected Access 2 is still widely used today and is considered the recommended minimum security. The final one is Wi-Fi Protected Access 3, introduced in 2018. It is the latest Wi-Fi security protocol that addresses vulnerabilities in Wi-Fi Protected Access 2 and provides enhanced protection for users. It uses simultaneous authentication of equals, which replaces the pre-shared key. It also uses stronger encryption, 192-bit in enterprise mode, forward secrecy, which protects previously captured traffic, protection against offline dictionary attacks, enhanced protection in open networks, and is mandatory in Wi-Fi 6 certified devices, and is the current highest security standard. Finally, let's compare the performance of different Wi-Fi standards. The 802.11b has a maximum data rate of 11 megabits per second and operates on the 2.4 GHz frequency band with a 20 MHz channel width, using direct sequence spread spectrum modulation, and does not support multiple input, multiple output streams. The 802.11a and G have a maximum data rate of 54 megabits per second. The A operates on the 5 GHz frequency band while the G operates on the 2.4 GHz frequency band, both with a 20 MHz channel width, using orthogonal frequency division multiplexing modulation, and do not support multiple input, multiple output streams. The 802.11n, also known as Wi-Fi 4, has a maximum data rate of 600 megabits per second and operates on both the 2.4 and 5 GHz frequency bands with a 20/40 MHz channel width, using orthogonal frequency division multiplexing modulation, and supports 4x4 multiple input multiple output streams. The 802.11 AC, also known as Wi-Fi 5, has a maximum data rate of 3.5 gigabits per second and operates on the 5 GHz frequency band with a 20/40/80/160 MHz channel width, using orthogonal frequency division multiplexing modulation, and supports 8x8 multiple input multiple output streams. The 802.11 AX, also known as Wi-Fi 6, has a maximum data rate of 9.6 gigabits per second and operates on the 2.4/5/6 GHz frequency bands with a 20/40/80/160 MHz channel width, using orthogonal frequency division multiple access modulation, and supports 8x8 multiple input multiple output streams. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.